Morning. Welcome to 2025, the first major MLPerf endeavor this year is MLPerf Inference 5.0, and I'm thrilled to be the MC and kicking things off. We've got a tremendous roster of folks who have all contributed in various ways to this round of the benchmark. We've got Scott, who will be who's helping to drive the show. We've got Miro and Michelle, our working group chairs, and then three representatives, each one speaking about 1 to 2 of the new benchmarks we've introduced in this round of MLPerf Inference. So thank you all for taking the time to join us. As a reminder for our friends in the press and analyst community, under embargo until April 2nd at 8 a.m. when we will be publishing everything. If we want to go to the next slide. For those of you in attendance, you should have a variety of materials. This time around, we've got the results in Tableau, which should have been sent to you, supplemental disclosures for MLPerf Inference, a press release, and then we have 3 blogs that sort of discuss the construction and motivation behind the new benchmarks that we introduced in this round. In addition, our Google Drive will get a recording of this briefing of the first half, I believe. I don't recall if we would transmit the Q&A. All right, so this is the agenda for the morning. I'll be giving the overview, try to get through it as quickly as I can so we can get into the heart of the discussion. Overview of the results, details on the new benchmarks, and then a Q&A with our submitters. So next slide, please. As an introduction for those who are not familiar, MLCommons is an industry consortium. We're a nonprofit, and our goal is better AI for everyone. We bring together industry and academia. We have over 125 members across 6 out of the 7 continents. I'm still looking for that elusive member headquartered in Antarctica. We're almost to 90,000 MLPerf results. And, within the MLPerf universe, we really focus on how do we measure the speed and efficiency of AI. And we have other initiatives as well that are focused on things like safety and accuracy. Although accuracy, it should be noted, is of course an integral component of both speed and efficiency, right? So we've got a variety of MLPerf benchmarks. Today, we will be talking about MLPerf Inference. And then MLCommons also has a big focus on data, right? Some of this is a consequence of building benchmarks. We need data sets to build benchmarks. That means we must curate our own. But we have also developed and released many open data sets, such as the multilingual spoken words corpus, people's speech, Dollar Street. And increasingly in some of our newer benchmarks, we've had to really construct custom data sets, particularly, or work with partners, particularly in the MLPerf Automotive working group. Next slide. Just to baseline around the goals of MLPerf, when we set out initially, we wanted to produce benchmarks to measure the speed of initially ML training, but eventually inference and many other things. We wanted to draw on both our academic and industrial heritage. We wanted our results to be replicatable, right? We wanted them to be fair and representative. We wanted to build benchmarks so that as people improved in the benchmarks, it would drive the most pressing workloads of our day, whether it's recommender systems, large language models, image generation, or object detection. We wanted to pick commercially relevant things so that as we drive the innovation forward, as we see more people coming through with techniques to accelerate performance, that it really benefits the whole industry. And we need to do this in a transparent and fair manner, right? This is a level playing field where everyone can compete fairly and evenly. And through that, the whole industry moves forward at an increasingly rapid pace, right? So those are some of the goals. If we want to go on to the next slide. Um, One of the things I like to remind people is that MLPerf at its heart is really a full system problem, right? Things like training a network to completion or performing inference are not just about hardware, right? Uh, Now, it starts at the hardware level. It starts with the transistors, the packaging, the fundamental silicon technologies that we have to construct these systems. But it is about architecture, right? In this round, previewing things we'll see later, right? We're seeing increasingly over time the use of new data types of things like matrix multiply units that can boost performance. Right, we see things like networking and storage, right? How we connect things together, and the scale of systems, and that's increasingly becoming a topic of significance in inference, right? Previously, in most of our training benchmarks, many of those systems operated at large scale, but some of the models that we see being used today do require a fairly significant scale in terms of number of processors, right? Power determines performance, right? Part of the reason for building a larger scale system is you can harness more chips, more power on a single problem, right? And of course, the algorithms, the software, and the data are critical elements here as well, right? Things like optimizing compilers play a very significant role in performance, improving the kernels that are used to express some of the fundamental computation in machine learning, different algorithms, right? We see this all the time where many layers of a neural network can be expressed in maybe a dozen different ways, and you have to pick the right one. You have to look at the right algorithm for fusing layers and how you uh, uh, perform broader scale optimizations. And lastly, it's a function of the data as well, right? We've seen in various submission rounds that things like sorting data is integral to performance. So as we look at the performance we get there, it's good to keep in mind all of these factors. So now I get to introduce my friend and colleague, Miro Hodak, who will be speaking on behalf of the MLPerf Inference Working Group. Miro, do you want to take it away?
Absolutely. Thank you, David. So yes, as David said, I will be on behalf of the MLPerf Inference Working Group. I will give you first overview of our benchmarks, then give you sort of a quick overview of the results, and we'll go over um, some of the key takeaways that at least are relevant to the cross industry and and the trends we see from the submitted numbers. So in terms of overview, the purpose of MLPerf Inference Working Group is to create and maintain a suite of benchmarks to evaluate performance of machine learning systems in architectural neutral, representative, and reproducible manner. Of those three, I would like to sort of point out the representative has been one that has been hard to keep up with the rapid pace of in the field, the new models becoming relevant. In each round now, we have to create a new benchmarks, and we've effectively increased the pace of getting new benchmarkings to try to be representative to the field. Now, the benchmarks that we have address both data center and edge systems, and the purpose of the benchmark is to get a measurement of how quickly the systems can run models across variety of deployment scenarios, which are on the next slide, please. So in inference, there are several fundamental ways of how that can be deployed, and that's why sort of single measurement does not really provide a good picture of what's really happening. So one such scenario is a server. And a good example of that is chatbot, right? So this would be a type of scenario where you have query arrivals with effectively randomly, but they need to be responded to within certain latency constraints. So in case of chatbot, the constraints would be when after the question gets posed, when does the first part of the answer appears, and then there would be another constraint as to where additional tokens and additional parts of the result will appear on the screen, right? So it's kind of a more of a flexible way of doing things. The other way of doing inference is offline. This is the case in which the system gets the entire batch of the data at the beginning. Clock starts and then clock stops when everything gets processed, right? So in this case, this is sort of a pure throughput, pure computational power type of test. And for our data center benchmarks, the submissions have to have both offline and server. If we are doing edge, then in addition to offline, there are two more scenarios that are applicable. One of them is single stream. This is a type of case where queries arrive one by one in a stream. So effectively, the system under test processes one query at a time. And multi-stream is kind of a variation on this, where you have actually several streams running at the same time that gets processed. And so in data center requires a server and offline scenario, whereas in edge it's usually offline and single stream, whereas multi-stream is optional, and again depends on a particular benchmark. If we can move forward. So there are several key ingredients that make up a benchmark definition, because while the working group puts together working implementation for benchmarks, it's really, the value really is in the specification of what the benchmark is, right? If somebody says that they want to just run a particular large language model, let's say, there are still a lot of ingredients that need to be specified. Even if you know what the model is, there are different checkpoints that needs to be done, right? So that's we need to specify what is the trained model. You need to know exactly what the input is, right? It's usually data set, what's the size of the data set, where is the origin of that, what's the pre-processing techniques, that all get specified within our benchmarks. And finally, once you have input a model, we also specify what the results should be. So we know what the expected output is, and the output has to come with the required accuracy. And we'll talk about the specific of this a little bit later. We have this specified for each benchmark. When you look at the results, you will find that we have two sets of results. One of them is closed, and another one is open. A closed is named because it has strict rules. So every submission has to conform to those rules, which really means that every submission solves the same problem, even if implementation is different, if different framework is being used, different numerical precision is, for example, being applied. However, the same problem needs to be solved to the exact same precision. And that means that the results from this section are apples to apples comparison. So this is really a division within which you can directly compare the results. We also have an open division, which has more permissive rules. It allows also different models than the reference one being used to solve problems. So this is really a division that allows a showcase for submitters to showcase their algorithmic or software innovation in general. However, the downside of that, because they solve different problems, the results are no longer comparable to the closed division results or between open division. And of course, the scope of the benchmarking is, as David said, is a full problem. So all the results sort of encompass both hardware and software component. Can move forward. So this is kind of the overview of the results in this current 5.0 round. If you look within the closed division, most of our submitters, 20 out of 23, have submitted in available data center division. We also have within the closed division, we also have edge and previous submissions. And in open division, you can also see several submissions. But as I say, by large, most interest for our submitter is it's the closed available data center. And in this round, we have no research development and internal submissions. You can go ahead. So this is sort of the full definition of each benchmarks. I don't have time to go over everything, but this is listed on our website, and also it's This is listed on our website. Also is part of this presentation. So if there's specific questions that can be asked in Q&A. But as I said, for every benchmark, what makes up each benchmark is the specific model, which is specified up to a particular checkpoint, a data set, quality that is accuracy metric, and the server latency constraint that is for server scenario in data center deployment. Let's go to the edge, which is the next. So for our edge workloads, we have a few less of that. There's some overlap between edge and data center. But there are also some unique cases here. And again, the definition is here based on the model, data set, and accuracy are listed here. Okay, let's move forward. So looking at the results, the total number of results is close to 18,000. The result in this content is any number that appears in either the spreadsheet or Tableau view that you have, and these have been generated by 23 submitting organizations. In terms of power result, which is very important, we have a power result from Fujitsu and Gate Overflow. The list of submitting organization is here. We would specifically want to welcome new submitters to our family of inference submitters, which would be CoreWeave, FlexAI, Gate Overflow, Lambda, and Mango Boost. Okay, continue. So what's new in MLPerf Inference 5.0? There are quite a few things. While there's a lot of numbers, the important thing is that we have 2 new large language model benchmarks, and we'll have overview of those. I just want to point out that Llama 3.1405 billion is the largest benchmark that we ever had, and it's sort of a type of large language model, truly large language model that you can see. We also have variation on Llama to 70 billion for low latency application, and we'll have a GNN type of network and also automotive network for edge. Looking at sort of new exciting hardware that we have results for, we have two processors that are appear straight as available. That is AMD Instinct MI325X. We also have NVIDIA GB200. We also have a processor available that was submitted as preview in previous round, which obligates them to be submitted again, so that they can the results can be fully validated. And those are Google TPU V6E, NVIDIA B200, and Intel Xeon Granite Rapids. We also have a new chip that has been submitted in preview, that is NVIDIA Jetson AGX Store 128. So forward. So there are several this many numbers. There are lots of stories that can be told and lots of sort of interesting insights that can be taken. But one particular thing that I think is sort of interesting in the whole content of MLCommons and sort of cross industry and sort of looking into AI is that we see evidence of sort of momentum around generative AI in benchmarking. Now, the momentum around generative AI I think is not surprising to anyone, but for a long time we've seen ResNet 50 as being the most popular benchmark. Effectively, that has been sort of a yardstick how you would measure the inference performance. And the reason for this is that the benchmarking community is generally fairly conservative. You need to have some sort of measure that you know how previous system performed in order to sort of estimate what will happen in the future. So you sort of want something that is stable, that has some history. And this is the first round in which we've seen that we have a new benchmark, and that is Llama to 70 billion, or we have a new benchmark that has the most submissions. That's Llama to 70 billion, which was previously included in around a year ago. We see that we now have 2.5 as many submissions as in the beginning, and we also can see as a chart over here that the number of results for the ResNet is declining, and number of results for Llama to 70 billion is is increasing in great pace. And again, that's basically demonstrated what I said. There's a, even in benchmarking community has now fully embraced large language models, and the true large language model measurements are used for performance evaluation. On top of just the more submitters, we also see dramatic increases in performance. As I said, this benchmark was introduced just a year ago. Compared to, if we look at the result compared to previous year, we see that median score that has been submitted has doubled. And we see that best score is now 3.3x faster than in the initial submission. You can go to the next round. And so it's kind of there are several reasons why this is, right? Why is such a dramatic increase, right? So one of them is that there's now system support for MXFP4 or FP4 type of format in general, right? Which only use 4 bits to represent the number, and that leads to faster computations. But what is important in MLComm and MLPerf results, you have to remember that our tests are not for just throughput; they also enforce pretty tight accuracy. So this is a demonstration of capability of this type of format, that even though you go to much lower numerical formats, the system are still able to produce results that are meeting our accuracy and quality targets. In addition, in this round, we compared to previous round, compared to the 4.0 round, we now have 6 newly available accelerator, and new accelerator generally brings better performance, hence the performance increase. We also, very importantly, have incremental software optimization. In each round, we see that the submissions, even if they use exactly the same hardware, the performance increases, there are significant performance increases, and all these three developments contribute to the increase in performance we've been seeing. The other part of insights is that MLCommons and MLPerf Inference working group works hard in keeping pace with the industry as more sort of models come in. We have, as I said, we had four benchmarks included, and these include 2 large language models, which represent the latest in the field. And I think for the next one, we have Jihan, who will give us overview of those large language models. So Jihan, please take it away.
Yep. Can you hear me?
Yes.
Okay. Yeah. Thanks, Miro, for the introduction to the MLPerf 5.0's results. My name is Jihan. I'm from NVIDIA, and I'm the task force chair for LLM benchmarks in 5.0. And I want to give you a brief introduction to the 2 new benchmarks we added in 5.0, which are Llama 3.1 Full of IB and the Llama 270B interactive scenarios. And first is the Llama 3.1 Full of IB. As Miro just said, this is the largest LLM we have ever introduced in MLPerf Inference. And while we formed the task force to create this benchmark, we have three goals in mind. The first is we identified the rapid adoption and increasing capabilities of large models like Cloud 3.5, GPT-0103, and also Gemini 1.5 2.0. And the second point in mind is we want to create a benchmarks that reflects the longer and longer context that's used to address the RAG, retrieval augmented generations, agentic AI, and advanced reasoning tasks that are like more and more popular. And the third is we want to have reasonable response latency to enable efficient and practical development in diverse scenarios, even for such a large model and a large context length. And the challenges for the submitters for this new benchmarks is such a large model, like full of 400 billion parameters, typically requires distributed inference on multiple accelerators or systems. So that requires a careful exploration of optimal quantizations and parallelization schemes that achieve high quality serving that balances the accuracies, throughput, and latencies. Next slide, please. And the dataset that we use for the Llama 3.1 Follow 5B is a mix of long bench, long data collection, ruler, and government summaries. So the task force has done extensive research in the area of long context inference, and the dataset covered long context comprehension, question answering, and info retrieval on the noise. And then the medium input and output sequence length is 9,500 and 750, which is very long compared to our previous language models, which is in the range of like hundreds. And we didn't sacrifice too much of the serving latency here. And in fact, we have 99 percentile time to first token of 6 seconds to address the long context and the huge model size. And the time per output token here is even smaller than what we previously have for Llama 270B, which is 200 milliseconds. And 175 milliseconds roughly translates to 6 tokens per second for the users. And that is already faster than the human read speed. And then we also show 2 diagrams of the input token length and the output token length distributions. So on the left side, we see that the distribution of the input token length ranges from 0 to 20K. And this is a very large diversification of the input. And then we are seeing very good alignment of the reference output token length from the Follow 5 model and the ground truth. Next slide, please. And in the next 2 slides, I want to talk a little bit about the Llama 270B interactive for low latency applications. The reason why we create the low latency scenarios for the 70B is to align with the industry trends and growing demands for low latency LLM inference in the real-time chatbots and agentic AI systems, which might require multiple inference rounds of language models. And then third is the deep reasoning models that has been very popular in the past few months. And the performance targets that we want for the interactive scenarios is we want to push for higher tokens per second per users, which corresponds to the responsiveness that the user is seeing. And at the meantime, we want to maintain high system level utilization and throughput, which corresponds to the cost efficiency that the API providers is seeing. And this creates a significant technical challenges for submitters, because you really need to balance the hardware and software stack optimizations to deliver both the optimal user experience, which is low latency, and high serving qualities, which is maintaining the accuracies and the consistency of the output. Next slide, please. And the task force has established the latency targets of the 70B interactive mode through analysis of the industry research, user surveys, and the performance data from leading platforms like ChatGPT and Perplexity AI. And we set the 99 percentile time to first token of 450 milliseconds, which is less than 1 second, and the time per output token of 40 milliseconds, which corresponds to roughly 25 tokens per second per users. And here I show the visualization of 5 tokens per second per user versus 25. So you'd see like the user experience on the right side will be significantly better, and it corresponds to what people are seeing average API providers nowadays. And I also want to stress that we are using 99 percentile instead of like 50 percentile, 95 percentile, because we want to ensure that user is seeing stable latencies even under high pressures on the server side. Yeah, and I want to pass on to Uday, which will introduce about the RGAT benchmarks.
Thank you, Jihan. Can you guys hear me? Okay. I am Uday Kurkure. I am from Broadcom. Next slide, please. Why graph neural networks? And why did MLCommons adopted a new benchmark in 5.0? Graph neural networks have been adopted in many domains: social networks, fraud detection, navigation, recommenders, drug discovery, chemical structure analysis. This is the workhorse of ML. Interestingly, 2024 Nobel Chemistry Prize went to Dr. Baker, Demis Hassabis, and John Jumper of DeepMind. Dr. Baker's protein MPNN leverages graph neural networks. Protein MPNN is a protein structure encoder decoder. And GNNs are particularly complex. There are very large graphs that do not fit into a single node memory. In addition, all computation is sparse computations, unlike convolutional neural networks in imaging domain or large language models use attention mechanism, but it's all dense computation. In addition, there is message passing between the nodes. Now let's look at the benchmark model that we neural network model that we selected. Our network model is relational graph attention network. That's what it is called, RGAT, multi-relational graph structure. And it is similar to attention. Attention is paid to the neighboring nodes. And most of us have heard of the famous paper, the attention is all you need. And here the attention is given to the neighbors, neighboring nodes, and relational graph attention differentiates between the edges. Next slide, please. As I mentioned, that most of the graph neural networks have are very large. The data sets involved are very large. IGBH stands for Illinois Graph Bench, and last H stands for heterogeneous. Heterogeneous means is all the nodes, most of nodes are heterogeneous. This is the largest public domain data set. It has 547 million nodes and 5.8 billion edges. And as you can see, there are author nodes, paper nodes, institute nodes, field of study nodes. So that's why it's called heterogeneous. Now that we have seen the data set, let's look at our model. Next slide, please. Model is a two-layer relational graph attention network. We use the fan out of a 15, 10, and 5. What it means is that in the first step, we chose 5 neighboring nodes randomly, and we process those. Then we go to the step 2, where we choose 10 neighboring nodes randomly. And then in the third step, we chose 15 neighboring nodes for each of the nodes selected. So that's why it's called the fan out. Next slide, please. Now let's look at the benchmark in a snapshot. Our task here is to classify graph nodes. Model is RGAT. Our data set is IGBH. Scenario in this round is offline. We may introduce server scenario later. Our validation data set size is 788,000 nodes. Our accuracy metric is 99% of the reference accuracy of 72.86. And performance metric is, as usual, samples per second. Even though this is the new benchmark, we got submissions on CPU, GPUs, from Fujitsu, Giga Computing, Intel, Lenovo, NVIDIA, Oracle, and Supermicro. I would like to acknowledge particular contributions from Intel and NVIDIA and MLCommons to develop this program. Thank you.
Hi, I'm Rod, and I'll talk about the automotive PointPainting benchmark that we introduced. Next slide. So when we're trying to decide to benchmark an automotive task, there's a lot of things we could choose from, because a vehicle in an autonomous driving space just has all kinds of machine learning and even non-machine learning things it can do. What we wanted was a task that was expensive computationally relative to the other parts of the vehicle needs. It's of course going to be something that's going to have a low latency and real-time inference requirement. It's going to need to maintain accuracy for safety, and we wanted something that was representative of different sensor modalities, so not just like pure camera, which is the most common case. So we chose 3D object detection as that task. That fit what we wanted for our requirements. And we decided on benchmarking point painting on the Waymo open data set. Point painting is a 2-part model, which I'll get to in a little bit. It's going to take 5 images from cameras as its input, along with 1 LiDAR point cloud, and it's going to process all that to produce 3D bounding boxes. And it's also a very image-heavy computation. Most of the workload is going to be in the images, and that's mainly because it's doing, it's processing 5 images versus just 1 LiDAR point cloud. And that fits our sort of our goal of what we wanted, where we wanted representation of different sensor modalities, in this case including LiDAR, but we wanted to make sure we cover the most common case, which is just camera heavy input. And so that's what we're achieving with this benchmark. And I'll mention separately from this work in the automotive group, we're also introducing a more comprehensive suite, and those submissions will be open soon. But next slide, I'll get back into point painting for inference. You can see the diagram of the model at the bottom. So on the left are the 5 input images that goes into a segmentation network. And in our case, that's DeepLab v3+. Those scores will be appended, or what's referred to in the model as painting, on a LiDAR point cloud. And that's going to be fed into a 3D detector. So that can be like a traditional LiDAR detector, in our case, point pillars. And that's going to produce final 3D bounding boxes. And I mentioned image-heavy computation comes from having 5 images being input to the model, but it's also because DeepLab itself is a heavier model. It has more parameters than point pillars. And so, here we're trying to just capture that the most of the workload is doing image stuff, which we know is what people are most interested in, but we still have some other sensor modalities which are in some vehicles. In terms of our metrics, compared to other edge benchmarks, we needed stronger requirements. For our latency percentile and single stream, we have a 99.9, and that's because, if you're too slow processing something, that could be potentially catastrophic, because this has safety requirements. So we gave a stronger latency percentile while still balancing the need for being able to run the benchmark in a timely manner. We wanted this benchmark to be accessible, and it can still be run within about a day. And then for accuracy, we also have matching some of the other higher end requirements and models, a 99.9 percentile accuracy constraint, maintaining with the reference implementation. And again, this is because this is a safety critical space. And that's our the point painting benchmark we introduced. And I think next is Q&A.
If I recall, that's back to me. I think the key thing so everyone should have a copy of the results in Tableau that you can browse through and sort of do some of your own comparisons. I know many of the people internally at MLCommons and at our member companies do plenty of analysis on them. So there's a huge amount of data to be digging through here, right? Nearly 20,000 results. So the first thing is we kind of put together a set of guides for how you can think about the results, when you want to do some analysis. And I think one of the first things that I always like to emphasize is submitting into MLPerf is a lot like running a marathon. Like, regardless of what your score is, you should be proud of it, right? It's a lot of work to get these systems tuned, to get the software ready, to get everything up and running, right? And many times these, are fully production systems, right? So there's a lot of readiness that goes into them. As you look at a lot of the submissions, one of the things we called out is that there were systems or processors that may have gone from preview to available. Oftentimes you might see a change in performance as software matures, for instance, right? You can look at the scaling over time, just how fast a benchmark has gotten, and we highlighted some of the sort of median and best case data earlier, but there's certainly trends to be had over time, right? Most of our benchmarks are designed to be around for, at least 2 years, and some certainly longer than that. And so you can see the trend in performance over time there, right? We're seeing new software stacks being introduced, as well as larger systems. In particular, as was pointed out, for something like Llama 405B, you know, you don't stick that on a single accelerator, right? And so that does lead to implementation choices. For instance, on some of the larger models, do you scale, for instance, within a single system or across multiple systems? There's all sorts of implementation choices here about how you deliver performance to the end user. All right.